So welcome to another session of 2019 AWS Public Sector DC Summit. Just have a few housekeeping items to share with you. We have the two exit doors right to the left. And to the left of the hallway, you have the bathroom. And then please remember to silence all your devices. This session is being recorded. So at the end of the session, we may have Q&A. It's important that you use the microphone. I could give you the microphone, or you could use the one right in the middle of the room. And the session recordings will be made available after this event. And also, please, if you have not already done so, download our AWS app for this summit. From there, you can share your feedback on each session you attend so that we can improve this next time you come here. With that, I'll welcome Anna, Pangeo, Praviti, and Rich Signet on stage for the next session called Community Tools for Analysis of Earth Science Data in the Cloud. Welcome, Anna.
Okay, hello everybody, and thank you for joining us. I appreciate you coming after lunch. I know it's a little bit tough. We're going to try to keep this as entertaining as possible so nobody falls asleep. So my name is Ana Pinheiro-Privet. I'm a senior program manager at Amazon. I'm actually not with AWS, but I'm with the sustainability team. But I work very closely with AWS, in particular with the Open Data team in a project that I'll introduce in a few minutes called the Amazon Sustainability Data Initiative. Today, in addition to this quick presentation that I'll give as an overview to that program and showing what are the opportunities to work together, if anybody is interested in pursuing that further, we also have Rich Signal, who works for USGS for 30 years, which is amazing. He brings a deep knowledge and understanding of the space of data and scientific data analysis. And he will be speaking today with us about Pangeo, which is a project, is almost like a community now, I would say, that is doing some amazing work and that we are very proud to be supporting. And so we're eager to see how we can move this space forward and do more with them. If possible. Okay, so I am going to try to find the tracker, which is right here, and jump straight into the Amazon Sustainability Data Initiative. So this program, we launched this program officially and publicly last December, but really we've been working on this with the Open Data team and other groups at Amazon for quite a while. And the goal of this program is really try to understand how do we leverage the scale of Amazon and our infrastructure and the knowledge and the technology to try to promote more innovation and problem solving in the space of sustainability. So not necessarily focus internally, how do we help Amazon, but externally, how do we help the broader community move forward in this space and remove some of the barriers that are preventing us from gathering more knowledge and more insight that is required. So just to provide a little bit of context, and when you think of a global sustainable development, we really need to think of how do we work that delicate balance of promoting economic development and prosperity, and at the same time, how do we preserve the natural resources, and how do we ensure, social fairness, and all of those aspects that sustainability encompasses. So for that, it's really critical that we have meaningful and timely insights to make decisions. So, but what we see is that although we live in a space and time where we have more data than ever, what we are observing is that that availability of data is not necessarily translating into the insights that we need to make decisions. And so that quote here is just something that I'm sure most of you have experienced, if not about the quote, about the actual fact that as a researcher or a developer or a scientist in general, most of the time that is required to extract some kind of insight from data is really spent on gathering the data, discovering it, and preparing the data for analysis, which really, if you think about it, if 80% of that time is spent on that kind of activity, there's a potential to unleash that time and effort towards producing more insights and more knowledge that can help us move forward faster. So what we're trying to do with the Amazon Sustainability Data Initiative is really to try to remove as much as possible that undifferentiated heavy lifting, as Amazon and AWS likes to call it, that will hopefully bring us all to a higher level. So, just for context, I was trained as a research scientist, and I spent most of my career doing research, so I felt that very strongly in my skin. Okay, so what the Amazon Sustainability Data Initiative is trying to do is really try to understand how do we work with the community to remove some of those barriers and decrease the cost and the effort involved in creating sustainability insights that can help us all. So we believe that by working on these three core areas, we can hopefully make an impact. So one is the data, which is at the core of everything that we're doing. And for that, we leverage the scalable infrastructure of AWS to make available data sets in the cloud and make them publicly available to anybody to analyze and access. And then we believe that, so by removing the burden of data acquisition and also democratizing access to the tools and the analytical capabilities that the cloud offers, together with, promoting knowledge exchange, we might be able to somehow move this space forward. Okay, so very pragmatically, what are we doing? So on the data side, we, as I said, we work closely with the community, not only with AWS customers, but with the community in general, and try to understand what are those foundational data sets that we should bring to the cloud that would really have the potential to unleash a lot of knowledge extraction. So the idea here is not, we don't want to move all the data sets to the cloud. We want to curate this space so that we bring the data sets that are really critical for this conversation, at least in this first phase. So we've been very focused on working with different data providers around the world to identify those data sets, those authoritative data sets, and then bring them to the cloud. And we do that through an existing program on AWS called the Public Datasets Program that Joe Flasher, somewhere here in the audience, is part of and has been a very active partner in this effort. And currently we have, I believe, over 40 data sets that span anything from like weather observations from NOAA and from different agencies around the world to climate projections, air quality, and these are just a few examples of the kind of subdomains that we are exploring so far. And we continue to grow this catalog in response to the needs that we identify as we work with the community. The other one is, as I mentioned, how do we democratize access to the tools? How do we ensure that, beyond the big institutions that have the data centers and the high-performance computers, we enable others around the world to have access to those data sets and extract knowledge? And we really work across a broad domain of audiences out there, so anywhere from startups to nonprofits and academia. So we are not just necessarily trying to encourage the research academics, but also the broader community to access these resources and try to see how they can innovate. So I was just going to mention, so as part of that process, we really try to offset the cost of experimentation. And to do that, we enable anybody that is interested in basically anybody that is interested in experimenting with an idea in the cloud that is related to sustainability. We have cloud credits and different grants that we offer for those that are interested. So if you want to learn more, please let me know. And this would provide access to all of the different tools and basically all the services on AWS that are traditionally available to the customers. Okay, and the final component, as I mentioned, is this idea of, okay, there's still a lot of barriers. We have to recognize there's still a lot of barriers for the majority of the people to move to the cloud. There's still a lot of legacy code that has been written, for on-premise systems. And so we recognize that there is an effort to move across, and we're trying to understand how do we remove those barriers? How do we make it easier for all of us to kind of learn together through this process and move forward? So we've been putting a lot of effort into not only just writing tutorials with our customers that are innovating to try to show what is possible and how they did it, but also create opportunities, for instance, to connect data providers with the customers and the broader community so that we can have a closer connection and exchange of knowledge there as well. Okay, that is all for me. I added a few links there and more information. Feel free to contact me or that address that as well if you have any questions or if you would like to get involved with this initiative. One last thing I wanted to mention before I give the stage to Rich is that so the Open Data team, as I mentioned, we're working very closely with them, and they have for many years been devoting a lot of their time and expertise to understand what is the optimal way to share data in the cloud to make it analysis ready and to encourage people to actually extract value from it. So they recently put together this guide that is called Sharing Data on AWS, which is really an interesting and very helpful example, guidelines basically of what are the things that they have learned. It's been led by Jed Sandwell, and he did a great job putting this together. So I have a few copies of this. If you're interested, come and see me at the end. And we also have it available on PDF format if you don't want to carry this with you. And I'll just mention that it is available at opendata.aws/guide. And again, if you come and see me at the end, I can give you that information. Okay, I guess that's all for me. I just want to mention that, Rich, please come on stage. I just want to mention that as part of that conversation, I was mentioning one of the components is how do we encourage people to experiment in the cloud? We've been providing different grants to different groups, and I'm very encouraged that the Pangeo group is also looking at how to potentially explore the cloud as a way to make it democratize access to these tools to the rest of the community. So thank you for being here.
All right.
Okay,
Awesome.
I have to go that way.
Yeah, thank you, Anna. So I'm really I'm happy to talk to you about Pangeo today. I think it's a really exciting project. Let's see. Is that the, no, okay. Yeah, okay. So Pangeo is a community platform for big data geoscience. I'm a research oceanographer at the U.S. Geological Survey, but I'm here representing this Pangeo community that consists of a lot more people than are on that slide right there, but those people have been very instrumental in leading the project and bringing people on board. So before I tell you about Pangeo, I want to tell you about what inspired Pangeo. This is a NASA simulation of the world ocean showing you circulation. And this model, in its most recent incarnation, it saved at 1 hourly time steps for a year, is 2 petabytes of data for this single simulation. So this is what inspired Ryan Abernathy at Columbia to start this Pangeo project, of sort of a selfish interest as an oceanographer. How do I work with data of this size? How do I share this with my colleagues? As most of you know, the ocean has absorbed 90% of the warming due to climate change. And so understanding the ocean is really fundamental to understanding how our planet is changing and what its response will be. So we absolutely need this kind of data to be in the hands of as many people as possible, so we understand it as best as possible. It can't be locked up in just the hands of the modelers who created this. And this was Ryan's inspiration. So I am at the U.S. Geological Survey. I also have a selfish interest in this project because I supervise a sediment transport modeling group. We have a coupled modeling system that goes from wind to waves, to circulation, to sediment transport that helps to tell us how the beaches and the coastline changes in response to storms and in response to climate change. So we have hundreds of terabytes of data that we want to share with we don't have petabytes, but we have hundreds of terabytes that we want to share with our colleagues. And we save this data from both of those models that you just saw. The data is stored in these netcdf files. The netcdf4 is actually a HDF5 file underneath. This is a scientific data format that was designed specifically for multidimensional data. And it's been with us for about 25 years. It's used extensively throughout the geosciences. And this is just showing you that on the left here, this is the vertical grid. So it's the main point here is in the vertical, it's not it's not a raster, it's not regular intervals. And in the horizontal field, it's also not regular intervals. This is not a 3D raster. It's more complicated than that. And of course, we're not alone. I've been talking about model output, and on the right is the CMIP5 archive, the CMIP archives, CMIP5 and CMIP6. These are the climate simulations. They went from 2 petabytes 6 years later at 150 petabytes. So for the next release, they're heading to exabyte scale. And on the left is NASA's projected cloud storage from about 50 petabytes now to over 300 petabytes in 5 years, or in 6 years. So everyone has this problem. This is remote sensing data. This is model output. But everybody has the same problem. So, this is still the way that most scientists do their analysis. They run their simulations somewhere on some high-performance computing facility, and then they download that data over a very fat pipe, hopefully, so it comes in fast to their local workstations where they store the data locally, and they have their software and their hardware that they maintain, and they do their analysis and visualization. And of course, they're limited to the number of processors they have. They can't share their data with it. That same workflows that they're executing can't be easily replicated. And the data has to be copied many times. We all know this. So what we want is is the data in the cloud, all the analysis and visualization in the cloud, and only a lightweight connection down to you sitting in the park with your laptop and your Wi-Fi hotspot, and you can do scalable data approximate analysis on your output. So what is Pangeo? So Pangeo is a community, first and foremost. It was started, as I mentioned, by Ryan Abernathy from Lamont in a collaboration with UCAR and the British Met Office, a very interesting collaboration, and with Google credits and funding from the NSF and their EarthCube program, and Anaconda here with providing Python support on some of the packages. But it was pretty quickly joined and expanded. There's a NASA Access grant that was a combination of the Washington eScience Institute and Element 84, and Amazon provided significant funding for that. Amazon also provided some funding for cloud credits for an ESIP project that I was involved with. And recently, Azure has entered in the Pangeo funding arena, funding Queens College for a quite significant amount to look at how to use Pangeo for ocean observations. And then there's a number of other groups many more logos than I could put on here. Actually, let's see, can I go back? I wanted to point out that this is a very open group. And in fact, if you go to their GitHub site, they tell you to add your name to this list. So here's the community, who you are, what you do, where you work, and you can put your name on this list. You just fork the repo, and you add yourself, and when they accept the pull request, you're part of the team. And you really are part of the team. You can participate in the weekly calls. Everything is discussed out in the open on GitHub. They really do not like you talking about the project via email or Slack. They want it as open as possible. And I think that's really helped this project grow. So what is Pangeo? Again, Pangeo is actually a software stack as well. The foundation is Python. So on this Python platform, the idea was, let's not build anything new. Let's take the things that are really successful out in the Python community already and make them really work well to solve these kind of problems. So on top of this Python environment, this Pangeo framework, it really fundamentally is a data model. I'm going to jump around here, but there's the data model of Xarray, which represents that NetCDF data model. And Iris is a similar package from the British Met Office. You can use either one of these. You can also use Pandas for tabular data. For handling these n-dimensional arrays, we use Dask primarily, which actually sits on top of NumPy. Probably should be modified a little bit. But this handles the parallel execution of code in this system. In the processing, you can use it interactively through a Jupyter environment. You can do batch or serverless. And you can run on HPC. You can run on your laptop. You can run on AWS, Google, or Azure. So you can run the same thing everywhere. It's cloud agnostic. You don't have to. And you can run it on your HPC if you're not ready for cloud or you have some other reason to do that. So this is the way we usually use it, though. These are the fundamental components, again, shown a little bit more clearly. This is the way almost everyone is actually using it. You have so this is HPC architecture. You have your n-dimensional array data and some distributed, bunch of files, perhaps, sitting on a file system. And those files are chunked into HDF, and NetCDF allow you to chunk your data so each little piece can be extracted separately, okay? And that's pretty important because this Dask scheduler then can have a bunch of workers go work on those little pieces of data and return them to Xarray. And this is the data, again, this is the data model. You can do this kind of crunching here with these tools. And then PyVis is the visualization piece that allows you to see, interact with the data visually. And all this can happen through your browser if you're using Jupyter so that you get this kind of experience. And I'm going to show you a demo later. The cloud architecture looks the same. As I mentioned, the only thing here is that this is an important piece. This n-dimensional array data that you've stored here on the cloud has to be in a cloud-friendly format. Otherwise, you get very poor performance. If you just move those netcdf files to the cloud, you get poor performance. And why is that? Well, Matthew Rockland, part of the Pangeo team, used to be at Anaconda, now at NVIDIA, wrote a really nice blog piece on this called HDF in the Cloud, Challenges and Solutions for Scientific Data. And he offered some various solutions. One is the cloud-optimized GeoTIFF, just do what the image folks do. But it turns out that doesn't work so well for us because we have non-raster data, and we also have, it doesn't really meet the netcdf data model, and also that basically gives you a chunk size of 1 in the time dimension. You're stuck with that, okay? So what else could you do? You could just stick those files on the cloud and pretend they're files through using Fuse. So just pretend they're files, and this is actually quite slow. Another solution would be to put those files on the cloud and use some kind of custom reader, get tricky with how you read them. Instead of using the existing libraries, do some fancy things. So the problem with netcdf is, and HDF is that you have to do lots of little requests. And that doesn't work so well in S3. You really want to load all the metadata at once and then just go after the chunks of data. So you could try to do some fancy thing like that with a custom reader. You could build a distributed service. Not too many people are interested in a data service. They'd rather go right to the S3. And then the last one is new formats for scientific data. And that's what I'm talking about with this ZAR format. So the ZAR format was actually developed in the genomics community, interestingly enough. And it was developed specifically to address these issues with HDF and netcdf and cloud. It's really simple. It's got a clear specification. Every chunk is a separate object. So if you think of all those chunks in a netcdf file, you take those out and you put each one of those chunks in a separate object in object storage. So, whoops, sorry. And so it's pretty lightweight, and all the data is just, all the variable metadata, everything is stored in just JSON. And then each one of these little chunks, you can have filtering and compression on that chunk using a very standard BLOSC library. It's all free and open source. And you can read that data just the same way you would read a netcdf file in Xarray. So from the user perspective, once the data is in ZAR, they can just use their same workflow. They don't notice. All they notice is that it works faster. So the ZAR format actually looks like this. This is another clever thing. So if you have 4 chunks here, the tag on object storage for chunk 00 is 0.0. Okay, so what this means is you don't have to have any fancy figuring out where the chunks are. You can just go exactly to the chunks that you need. And so if you look at the metadata, so it's just JSON, as I mentioned. There's 2 attributes. So if you look at a data set like this AddCirc data set and a particular variable like zeta, you'll find these 2 things, Z-array and Z-adders. And the Z-array just tells you the chunks and what kind of compression was used, things like that. And the attributes provide all the other sort of netcdf-like information that tell you, OK, this thing called zeta is actually water level elevation above geoid, OK? These are the things that make up the CF conventions. So this is very simple. And probably the most important thing, I think, actually, and sort of overlooked perhaps, is that this is really truly community-driven. So if we want a format to save all of our scientific data for the long term, do we want a complicated data format that's only held by, tightly by one group, development group? Or do we want something that is, and only maybe 2 or 3 people understand the library that reads that data? That's a little scary, I think. I'd much rather have something that was community-driven. The people who have contributed to this ZAR package are some of the rock stars in this community. And there's a bunch of more, so it's developed out in the open. What do you think about this new enhancement? Well, there's discussion back and forth on GitHub, and then something gets implemented. So I'm very, very hopeful about the ZAR format. So now we'll get into actually actually looking how this has been used. NOAA had a big data project where I think you might have heard some of the previous talks here at the summit. about how a lot of data, environmental data, was moved onto the cloud, and NOAA provided the data, and the vendors, the different cloud vendors moved it onto the cloud and at no cost to NOAA. And so, whoops, sorry. So with this National Water Model 1.0, okay, what it predicts the discharge on 2.7 million rivers, and there's a 1 kilometer grid for the US that has all the forcing parameters and everything. So altogether, about 1 month of forcing and output is about 15 terabytes, and it was pushed to the cloud, so it is out there in buckets, but it's in netcdf files. And this 25-year analysis, it consists, though, if you want to go look at the river forecast data, the hindcast data for that period, it's 230,000 hourly netcdf files. So if you try to extract a time series from that, you're going to be disappointed. So the idea behind this project was, let's take some of this data and put it back on the cloud in a cloud-friendly format and see what the performance looks like. So, so this is what we did. So here's just a simple test of reading some data, taking the mean of some data, and this particular data set, it was 23 gigabytes of data, and we ran it, and it finished in 2 minutes. This was just pretending they were just regular files, and if you do the same thing with ZAR, it's the exact same data set, and we take the mean, and it's 12 seconds. It's 10 times faster. If it was 10% faster, nobody would care. 10 times faster is kind of a big deal. So this is just showing reading some National Water Model data from ZAR and going through and computing the maximum temperature over the US for a week of data. And again, this is the test we were doing before. It finishes in just a few seconds. All right, so I'm now going to do a live demo, because I don't think I've seen a live demo yet, and it's Wednesday afternoon, and it's always entertaining to see if it'll work. In fact, my laptop is locked, so I have to unlock that first. All right, so we're going to use everybody's favorite search engine, DuckDuckGo, and we're going to type in. So this is something you could do yourself. Don't do it right now, though. Listen to me. Reproducible notebooks, GitHub. Okay. Clearance on notebooks. That's not the one we want. We want this one here. And so this is a bunch of, this is a organization with some repositories where each one of these things can just be executed by you. You can download the code. If I click on this, it'll bring up the repo. And you can see that all is in this repo is a IPython Jupyter notebook and some configuration that specifies the software environment. But all we're going to do is go down here and we're going to launch, we're going to click on Pangeo binder, which is going to launch this, hopefully, on Amazon Cloud using this binder instance. And what it does is it actually takes that the specifications in the repo, builds a Docker container, and then the Docker container is launched into this environment. So now I have a notebook. So I didn't install anything, right? All I did was go to a link and execute that. And now I'm on the cloud, and Pangeo is paying for this. So I executed a cell that just imports some libraries, and now I'm going to. Here, I'm going to move up a little bit, and I'm going to start this cluster up. So the only thing that's different on the cloud, besides, for this whole workflow, if you're on a local machine, you say local cluster, and you use however many CPUs you have on your machine. If you're on HPC, you can launch a cluster on your scheduling system, like Slurm, and it'll actually request a whole bunch of workers, which will then come back and form your cluster. And on the cloud, we're using Kubernetes, and so we can just request. Actually, hopefully, I should have executed this next. Well, OK, we already got the 30 workers and the 60 cores. And now I'm going to execute this next cell, actually, which adapts the workflow. So you can see, if we need these 60 workers, they're going to work for us. If we don't need them, they're going to disappear. If I execute the next cell, because I'm not really doing anything, probably this cube cluster is going to OK, so now it's back down to 0. Okay, so I wanted to show you how it can adapt dynamically, and that's important, obviously, for cost. So I've got my client. I'm going to scroll down a little bit here. Can people see this? Yeah, OK. And so now I've just got some logic. Well, am I on Google or am I on Amazon? I'm on Amazon, so I open up that particular bucket. And after a few seconds, I can then look at this data set that I've opened. You see I've opened it with Xarray OpenZar, okay? And actually, let's just insert a cell here below so you can actually see the data set. Oops, where did I type that? So here's the data set that we loaded. So it looks just like NetCDF. It's got time coordinates, X and Y. It's got these different variables, okay? But we haven't really loaded any data yet. So a bunch of attributes. And then we took a look at this particular variable, zeta. Okay, I'm going to execute that again. It's this water surface. It's got 720 time steps and 9 million nodes. And its chunk size, okay, is 10 in the time dimension and 140,000 nodes. Okay, so these are nodes of triangles. This is a triangular mesh. This ocean, and you'll see when we visualize this, it's a very detailed mesh of the Gulf of Mexico, and we're looking at Hurricane Ike water levels. We're going to try to find the maximum water level during this storm. So, we're going to go down here, and we're going to see how big this variable is. It's 53 gigabytes, okay? And so now we still haven't done anything. So the next cell that I'm going to execute, the next cell is a comment. The next cell is going to be taking the maximum over the time dimension. This is Xarray magic, right? And I'm going to persist this onto the workers, so that if the data is going to go onto the workers, if I need that data later, I might want to use it to calculate, say, the minimum, okay? So here I'm going to execute this cell, and now we're going to actually start doing some work. And actually, while that's running, I'm going to go back and I should have opened up the dashboard so we can see the workers. So the horizontal lines here are the different workers, and now it's adapting. It's saying, hey, I need some more workers. This is a big job. So every one of those horizontal lines on that upper right plot here is actually one of those CPUs reading from ZAR, getting a chunk of data. So the worker goes and gets a chunk of data and computes the maximum for that chunk, and then it's aggregating it back together with the rest of the chunks, and then putting it back together for the user. Now, all the user did was say, hey, give me the mean, or give me the maximum water level, and Dask and Xarray handle all the rest of the work. So this is stuff you used to have to do, explicitly. And so we got this result back. It took 43 seconds to crunch 50 gigs of data. It would have taken 60 times longer if we did that with a single core. And it doesn't matter on the cloud, right? It doesn't matter whether you use one. You can use one core for 60 minutes. You can use 60 cores for a minute. You pay the same. Right? That's the beauty of the cloud. So here I'm just going to load some visualization, this PyViz package I was talking about. I'm just going to execute all these cells. But the magic here is this, again, this tri-mesh. So I have a bunch of triangles. I have some data on a triangular grid. I'm going to just say tri-mesh. And then I'm going to say, hey, I don't want you to render 9 million polygons into my browser. That would crash my browser. I want you to rasterize the result of those polygons onto a window that I'm going to specify here, to be 600 by 400. So that's what happened here. With those 2 lines of code, I generated not just a plot, but an interactive visualization here, which I'm going to show you. So here's the result. Here's the maximum water level during Hurricane Ike. We see the tides in the Gulf of Maine, which we don't really care about, right? That had nothing to do with Hurricane Ike. And we see this little blob down here that we can't really tell what it is. Something happened down there. So let's zoom in. This is, again, the magic of PyViz. So I'm going to just zoom in here. And when I zoom in, you're going to see the original grid. And now on the back end, Python is re-rendering and delivering back the higher resolution. Let's do it again. This is a really detailed grid. I'm going to zoom in again. It's going to re-render again. And now you see the full resolution. This is awesome. We couldn't even render these models in the browser before. And now we've got we've got this tool where we can do all of our analysis. And we can do this scalable data approximate analysis, and we can visualize the results interactively. We really can sit in the park with that notebook. It's amazing. So I'm going to switch back to the presentation, hopefully, and just do, let's see here. Okay, I'm going to skip over these because I didn't need them. I just want to point out that this is not just for model output, as I mentioned in the beginning. If you check out Pangeo and Medium, there's a bunch of great blog posts. And one of the really nice ones is this one by Scott Henderson, who is working on that NASA Access grant. and with AWS funding. And he's doing Landsat processing with Pangeo. Okay, well, it could work with any imagery, but he's got this really nice blog post about doing this work. And this is just one image from his blog post showing Landsat, this sort of the hello world NDVI calculation. But the cool thing here is what he says, what is special about this example is that the analysis is easily reproduced, scalable, and interactive. 100 gigabytes of Landsat 8, basically just using the data right from S3, not using any fancy tools, just using Python to crank on this data and do what you could do in Google Earth Engine, but in a completely cloud agnostic and open way. No copies of the data were needed. And it's not just for geoscience data. Actually, we might have to change our title slide. There's people using it for, there's people using it for neuro data and neuroscience data. We're using it, and it's not just for big data. This is a machine learning class that we actually did at USGS, sponsored by our Community for Data Integration, where we had these 2 training workshops. It wouldn't have mattered how many students we had because we just scaled up with Jupyter Hub, and we could have all the data, and the training was on the cloud, and so they could just use their notebooks. They didn't have to spend the first half of the first morning trying to get everything installed. So just a little note about how we deploy Pangeo on AWS. It is, as I mentioned, on Kubernetes on all the clouds, but on this, we're using EKS. And there's 3 classes of node pools for the geeks in the crowd. This is the core pool, which runs Jupyter Hub. And then there's an auto-scaling pool to handle like the number of users that, for each notebook. And then there's this Dask pool of workers that I was talking about. And when you saw those workers get added, those are in a pool that it can be preemptible. So they're on spot instances because if we lose those workers, just another worker will pick up and keep, they'll just keep going. So it's installed with a Helm chart. There's full instructions at Pangeo.io. And as I mentioned, repo to Docker is used to make it really easy for people to customize their environment and create a Docker container that's appropriate for their discipline. Okay, so overcoming barriers to adoption. There's still some barriers. A lot of people, when you talk to about this stuff, they're concerned about cost. And in fact, at our institution at USGS and at our sister academic institution in Woods Hole, they have a program where HPC is basically free for research, but yet the cloud is you pay full price. So trying to get researchers to use the cloud when you have that kind of a model is not too encouraging. So I'm hoping that institutions will start subsidizing cloud research the same way they subsidize HPC, because there's really not a lot of reason to stay on HPC these days, in my belief. Anyway, there's things that there's things that I think Amazon is doing that are really helpful. These research credits, obviously, for letting people experiment and see what this would look like for their workflows, and waiving egress charges for research. There's various sort of approaches to that really help, because sometimes researchers want to work on a big data set on Google Cloud, say, and on Amazon Cloud and combine the results. There's egress happening there. The new skills that are required are a challenge. I think these AWS, I went to like a one-day training workshop in Boston on containerization that was super helpful. Obviously summits like this are super helpful, although you don't see too many research scientists here probably, right? We've got to get the word out to them that this is a will have major short-term impact on their ability to do science. These hackathons that are held, like science hackathons, have been really useful. And I think these sort of institutional roadshows can be really helpful, where someone who knows about this stuff, like I could go into some university, give a talk about how this is important, and what impacts this. I could meet with their scientists. They might listen to me because I'm a scientist, and we might actually get them on board. So, and then the data formats, people are worried, are these things going to change? How stable is this czar thing? And so I think that'll just happen. That'll naturally, the community will come together, I think. And if we publish our benchmarks on these things and we blog and we present, eventually it'll happen faster. So finally, Pangeo is a movement. Come visit us at pangeo.io. Read those medium.com articles. You can chat with us on Gitter, and please come help and join us on GitHub. Thank you very much.
I think we have some time for Q&A.
I'm going to ask a question, and then maybe we can open the survey. Thank you. Yeah, so I was just curious. You show the increment in the size of the CMIP data, which is a critical data set for, climate risk and assessment and, like in adaptation. So 150 petabytes is what I guess the community is respecting the CMIP6 to be. Is Pangeo planning to do anything to enable access to the data and make it more accessible to the broader community?
Yeah, absolutely.
Yeah,
there is a lot of, I actually didn't talk about the climate folks who are involved with Pangeo, but there is a movement to move some of the CMIP6 data to the cloud in ZAR format. But the sustainability program would be, really exciting to get some of that on there. And I guess you're not just providing the space, but you're providing some of these other parts of the environment that can really help researchers. I think that'll be huge. I think once you don't have to move it all there for people to see the value, and then maybe when they see the value, then we move it all there.
Great, thank you. So I would like to see if anybody have any questions, either for Rich or myself. Please feel free to maybe raise your hand, and we'll give you the microphone.
Someone.
Hello, I'm Anil from University of Maryland. I work with the Department of Geographical Sciences. We do a lot of NASA Landsat data processing. So I guess my question is for you, Anna. So as you saw, the scale of data is pretty high. It can go into 300 petabytes in coming years. Would AWS be hosting all of that on S3? Or would it be on a deep glacier or someplace you have to wait to access it? Because that's a realistically the scenario we are looking at. And right now, I know NASA has been moving their data sets to AWS like we just learned. So I'm trying to understand, where does the data actually lie in AWS environment? Is it on S3 or is it on deep glacier?
Yeah, so I'm not exactly the best person to answer that. I wonder if Joe Flasher is in the audience.
Actually, I can take that question.
You can. Okay.
Yeah, I'm a solutions architect. So S3 has unlimited size for data storage. Literally, you can host any amount of data in it. Now, Glacier is a subset of S3. So we have S3 standard, where you have the frequent access. That's a different pricing model and different speed of retrieval. Then we have the S3 infrequent access. So it depends on how they're accessing that data. They can move in between those. And then the third one is the Glacier. And we actually have Deep Glacier, which makes it like 4 different storage classes. So it depends on the access of the data and the design of the architecture. They can move those data in between those, and within those, there are different pricing models and different speed of retrieval. So it's S3. I mean, I can't say I don't work with this data. I'm just telling you that the power of S3 can host infinite amount of data.
So I can add that USGS is working on moving the data to the cloud as their own activity and working with us on that. I don't know exactly what the timeline is, but we can put you in touch with the people if you're interested specifically about the Landsat history. Thank you.
I can take your card if you have your card. Do you have your card? No? Okay. I'll give you mine, then you can reach us. Do we have another question?
There's a question in the back there.
Okay.
I cannot see anything from here.
I know.
So, Anna, nice session, and Rich, really nice presentation. Couple of quick questions. One is, how do you search for data in Pangeo? I assume in this case you knew exactly what was there on the S3. Does the catalog have to be changed because the catalog is designed for files, and now you are looking at, ZAR is different objects. And the second question is, how do you do batch processing? I know you mentioned batch processing. A lot of people are still used to processing files in the batch mode. Does Pangeo support that?
Yeah, so the first part of the question, there's definitely a need for a catalog. You know, I think whoever, you know, depending on who you ask in Pangeo, you'd probably get a different answer. But I think that, you know, if you go to something like data.gov, you know, which you might hope would be the place you can find all the data, you'll find all these data services, and you'll find some, you know, URLs for different sites. I mean, why not? Why couldn't, you know, that could easily return a URL for, you know, an object like a ZAR file, right? Or a ZAR data set. And so actually we did that little experiment. I worked with Andrew Pawlowski from Element 84 last year at the developers conference. We actually, and actually the whole, it's just, that's all you have to do. It's just a different type. You know, it's just so you can certainly use all the search capabilities that we currently have. You just have to know, like when you find this thing, you know, in the metadata, you have to identify this with enough information that you know what to do with it, you know, when you load it. So, you know, you have to be able to represent that as like, you'd like to be able to represent it as something you can load as a netcdf CF, you know, data object. But then you have to identify whether it's in, you know, Azure or Google or Amazon or whatever. But really, I don't think it presents any particular challenges. But in Pangeo, and specifically, we kind of looked at Stack a little bit, which Stack is being used in the remote sensing community a lot. And then there's an intake, which is sort of a Python-centric thing. There's a stack to intake catalog thing. So that's one way you can find data. You know, like Scott Henderson's demo, if you go look at that, it's using this stack intake connection to actually locate all the scenes, you know, that are needed. So that's all working nicely. What's not quite working perfectly yet is cataloging of like the ocean model output and all the climate data and stuff, but we'll get there. Oh, and the second, what was the second part? Oh, the batch processing, yeah. I mean, so this is just Python, you know, so you can batch Python, and you know, there's no particular issue there.
So how does Dask handle the actual job? That's the question, right? The
Sorry?
Dask is handling the I/O on the multidimensional access.
Yeah.
But when you're doing a batch processing and you're trying to scale it out, then is the responsibility back on the programmer who's creating the Python code, or how do you do that? And,
No, I mean, Dask can handle it just the exact same way.
okay.
Yeah.
Any other question? Thank you, Rich, and thank you, Anna.
Thank you.